Thank you very much, Vanessa. I'm very happy to be here, and I hope I'll soon have a chance to visit Barcelona physically. But in the meantime, let's start this remotely. So as Vanessa said, I'll speak about Blinder, which is a protocol for robust anonymous broadcast via MPC. And this is a joint work with Ittai from VMware and Benny Pinkas from Bar-Ilan University. And also this work will appear in the upcoming CCS conference. So let's start. In the secure broadcast problem, we have a network with multiple parties. One of them is the sender, and it has a message. There could be also malicious participant in the network, and we assume that they follow a single strategy that is led by an entity called the adversary. The goal is that the honest parties obtain the sender's message, even when the malicious parties try to interrupt. So there are three main approaches to solve anonymity. We have onion routing, which relies on onion encryption. We have mixed network, where each mixer collects a bunch of messages and transmits them in shuffle manner. And we have DC networks, which propose a theoretical way to obtain strong security guarantees, even against a global network adversary. The first two typically benefit a low latency. However, they usually rely on complex adversarial model. They are also prone to statistical attacks that depend on the network topology and corruption strategy. Systems like Dandelion follow a collective definition of security, but the security that specific user is provided with is not well defined. In addition, efforts to bring strong security to mixed networks using differential privacy or attempt to detect a corrupted mixer using some kind of loop messages are still very limited. On the other hand, DC networks follow a simpler threat model and enjoys a stronger security, but suffers from higher latency. This is because it works over full graph networks. To improve that, recent works shifted to the client-server model, which makes the communication graph much simpler and significantly reduces the latency. Sorry. Blinder is also a variant of client-server DC network, but it also proposes several improvements. So it is a natural question to ask who needs such kind of anonymity guarantees. So first, a UN report from 2015 states that encryption and anonymity enable people to exercise their right of freedom of opinion and expression and the right to privacy in the digital age. So they urged countries to make sure people are free to use such tools. Second, we wished whistleblowers could remain anonymous in order to effectively fight corruption. Third, it's obvious that payment systems like Monero and Zcash, which are anonymous in the application level, they require to use also anonymous communication in the network level to be robust against traffic analysis. Last but not least is our recent results in differential privacy that analyze the shuffle model, in which users provide inputs anonymously. So this model resides between the curator model, which is the classical model, and the local privacy model. And the shuffle model lies in between, and it benefits better trade-offs between privacy and accuracy. We can benefit from the use of MPC in two ways. First, the threat model and security analysis become simpler compared to the previous works based on mixed networks or onion routing. And second, we can use the state-of-the-art techniques for computing on secret data. So as I'll show in this talk, this becomes very handy. Our security definition is given by the anonymous committed broadcast functionality. So from this functionality, we can extract the guarantees of our protocol. we do this by first looking at the functionality when run using a trusted party. So first, we denote the number of clients by capital N. Then the trusted party initializes an empty table with N entries, and each client sends a message to the trusted party, and the trusted party appends it to a random entry in the table. Finally, the trusted party shuffles each entry in the table and opens all the content of the entire table. Okay, so here the table is A. So from this implementation of the functionality using a trusted party, we can observe several properties. The first one is correctness, which means that the messages that the trusted party reveals are the same messages that are sent by the clients. Now, you can also note that once a client sent a message, she cannot regret, because there is no such feature in the functionality to allow a client to regret. So this property is called commitment, and therefore we call our functionality anonymous committed broadcast. Now, anonymity means that nobody but the trusted party can associate a message to its source client. In addition, it's impossible to make the protocol crash, nor prevent a client from sending a message, which we call censorship resistance. So our claim is that Blinder, our protocol, emulates the operation of a trusted party, and emulation is an MPC notion, which means that the emulating protocol and the execution within and the execution with the trusted party have the same security guarantees. So whatever we can achieve with the functionality when implemented using a trusted party is also achieved when implemented using the protocol. So the contributions of this work are as follows. We introduced Blinder, which is a client-server-based protocol for anonymous broadcast, where the servers run a secure computation protocol in the honest majority model. And in our setting, this means that the adversary may maliciously corrupt up to a quarter of the servers. In addition, it may corrupt a small fraction of the clients and inspect all network channels. Yet, the adversary cannot halt the execution of the system or prevent honest clients from broadcasting messages. We demonstrate that Blinder has a very low latency compared to previous systems in the same model, like a Riposte or Honey Badger. In particular, the Blinder protocol is amenable to a GPU implementation, which drastically reduces the latency. So let me turn to the high-level idea of the protocol. The protocol works in epochs, such that in each epoch, the servers collaboratively maintain a large table of messages where the table is initially empty. And epochs can be split either by an agreed upon time interval or by some number of accepted messages. The content of the entries of the table remain hidden from the servers, such that only if a large number of corrupted parties collude, they will be able to see the content. And we do this using Shamir secret sharing. So each server has a Shamir sharing of each entry in that table of secrets. Then, to allow a client to input its message, she plays as a client in a multi-server private information right, or PIW. The client picks a random index in the table and requests to write its message to the table entry with that index. We call this request a blind message. What's important in blind message is that the servers must not learn to which index the client is writing. Now, the blind message in the protocol, it has a specific format. So when the servers receive the blind message from the client, they have to verify that it complies to that format. And they do so using a simple MPC protocol. Now, after processing the blind message of all clients, the servers reconstruct the secrets in all entries. So the servers see the messages in a random order, which reveals nothing about the source of each message, the source client of each message. So in the rest of this talk, I'm going to show you how to obtain those three building blocks: Shamir sharing, private information right, and MPC. It's constructive to start with a single server private information read to see, as a stepping stone towards the private information right of Blinder. In such, so how do we build such a scheme for private information retrieval? We will use an additively homomorphic encryption scheme. In such an encryption scheme, having an encryption of X and Y, one can obtain an encryption of X plus Y, or in general, an encryption of any linear function of X and Y. Like in this example, there is any, it can obtain alpha X plus beta Y for any alpha and for any A and B, sorry. Now, in PIR, the server holds a table with n entries, and the client wants to obtain the I entry of the table without revealing the index I. Suppose now that there is a key pair PK and SK such that the client has both keys. These are the encryption and decryption keys. And the server has only the encryption key. So the scheme goes as follows. The client forms a vector of size n, with each entry contains an encryption of zeros, except the I entry, which contains an encryption of 1. The client sends the vector of encryptions to the servers, to the single server, and the server computes the encryption of a dot product between the vector of encryption that it got from the client and the table that it already holds. And it can do so due to the homomorphism of the encryption. Then the server hands back the result to the client, and the client can decrypt the result, which is exactly the content of the entry the client wanted to get. So we saw how read works. Now we can see how write works, which is quite similar. Here, the client wants to add delta to the third entry of the table. So again, the client sends a vector of encryptions to the server, but now instead of encryptions of 1 in the third entry, she puts an encryption of delta. The server uses the additivity property of the encryption again and updates each entry by adding the encryption given from the client. Now, the communication and computation of both the client and the server is order of n, which is the size of the table. And observe in this scheme that it only supports one client because it works with encryption keys. So the messages that can be written to the table should be compatible with each other in terms of being encrypted using the same secret keys, the same encryption keys. Sorry. So yeah. So to overcome this challenge of supporting more than one client, there are some private information right schemes that extend the scheme with more servers. So now each server has its own table such that the local entries of the servers are shares of the real secret value. For example, in this picture, we have x1 and x2, which are the shares of some secret x, such that x1 plus x2 equals x. Now, to add delta to location 3, the client randomly generates 2 tables, such that the sum of each entry of the tables equals 0, except the third entry, which the sum of that entry in the 2 tables equals delta. Then the client sends 1 table to each server, and in this way, a single server doesn't have enough information to understand what values are hidden in the entries. Now, this naive scheme can be easily extended to more servers, but even though it is still has some limitation. So I will describe those limitations next. So first, the communication for serving a single client is linear in the size of the table, which in turn is greater than the number of clients. So the complexity for all clients would be quadratic. It would be quadratic, of course. And it becomes the bottleneck when the number of clients is very large. The second thing is that a single corrupted server may cause a denial of service attack, because even if the server becomes unavailable, the rest of the shares of the other servers become useless. So robustness solves the first problem by reducing the blind message size to square root of n. However, it is limited to 3 servers only. It is not robust and not censorship resistant. Blinder solves both issues, extending riposte to any number of servers. And the only compromise we make is on the threshold of corrupted parties, of corrupted servers. So while riposte and other works, the threshold can be n-1, which is the optimal. In Blinder, this must be at most quarter of the number of servers. Our private information right relies on Shamir secret sharing. So in the Shamir secret sharing, we have a dealer with a secret S, and she wants to divide it to n pieces such that t or less pieces would reveal nothing about the secret, and t+1 or more pieces are sufficient to reconstruct it. For example, if we take n equals 5 and t equals 1, where n is the number of total number of servers and t is the number of corrupted servers, the dealer chooses a random polynomial of degree t, which is 1 here, and sends server I the evaluation of the polynomial on the value I. And we call this value that server I receives the share of server I, Si. So in this case, we have shares S1 up to S5. Obviously, a single server who has only one point on that line cannot tell anything about the line, because the line could be anything. But 2 or more servers can interpolate the polynomial and find the correct line that passes through all points. Now, this way, they reveal the secret by checking where the line crosses the y-axis, right? So the secret S is where that line crosses the y-axis. Now, for some notation, the sharing of S is the list of shares that the servers obtain for a secret S, and it is denoted by square brackets. It is well known that the servers can find the line even in case the corrupted servers provide wrong shares, because they have enough redundancy. So in this case, even if we have one corrupted party, one corrupted server, it doesn't make the protocol to abort, because we still have 4 other correct points on that line by which we can interpolate the correct line. And this is a key property that helps Blinder to achieve robustness. Now, secure computation allows to perform computation on secrets without revealing the secrets. So given sharings of x1 to xk, the goal is to compute some function f on the secrets without revealing them. The idea is to break the function f to simpler functions. Specifically, any function can be described by an arithmetic circuit that consists of additions and multiplications. In the context of MPC, we distinguish between linear operations and nonlinear ones. So addition of 2 secrets, addition of a secret and a public value, and multiplication of a secret and a public value are linear operations. And these linear operations can be performed without any interaction between the servers. On the other hand, multiplication of 2 secrets is nonlinear, and this requires communication between the servers. Now, the communication complexity for a single multiplication operation is constant per server. So private information write via MPC. So how can we do this? Suppose the servers expect to serve 9 clients in one epoch. So they initiate a table of size 9, and such that each entry has a sharing of 0. Now, for each entry, each server has a share of 0. So we denote this table of secrets by global table, and the tables of shares that each server has by local tables. Now, in this example, the client has a message with the value 13, and it chooses to write it to the table index at number 7. To see how we get the square root complexity in our scheme, instead of a single dimensional table, we work with a 2-dimensional one. So each entry has X and Y coordinates. So in this example, we have 3 by 3 table, and the index of the clients, it was 7 before, and now it becomes 3, 1. So the client generates a row and column vectors, each of size square root of n. She puts the value 1 at the X coordinate of the column vector, and the message at the Y coordinate of the row vector. Note that when multiplying the column and row vectors, we get a 3 by 3 matrix with the value of the message at the chosen coordinate, X, Y. So here is 3, 1. So the client generates the 2 vectors, and secret shares each of the entries toward the servers. Okay, so this is the first step. The second step is having the servers perform MPC over the vectors, and they obtain the full matrix for that client. So the client only sends the short vectors, and the servers, like they blow it to the full matrix. Now remember that the servers do this without revealing any information about the values in the short vectors, and therefore they learn nothing about the location of the message that the client picked. Now the communication complexity for getting the full matrix is order of n, because we have n multiplications. We multiply each entry in the row vector with each entry in the column vector. So the servers, in the final step, they add the matrix they obtain from the client to the global matrix that they maintain like from the beginning. And in this example, we have that the global matrix becomes exactly as the matrix obtained from the first client, because it just was the first client, and beforehand everything was 0. So as another example, we can take the second client. The second client has the message 84, and the location that it chooses is 2, 2. So it puts 1 in the second coordinate of the column vector, and 84 in the second coordinate of the row vector. Now the servers securely multiply the vectors and obtain the full matrix of that client, with the message appears at location 2, 2. Then the servers add that matrix they obtain to the global matrix they had from before, and the result global matrix has exactly 2 messages now. The first one from before, and the second one is from the second client in location 2, 2. So it is clear now how to obtain blind message with size square root of n. And the blind message size actually the communication complexity between the client and the servers. However, note the communication complexity between the servers themselves for obtaining the full matrix of a single client is order n. Therefore, for all clients, this would be order of n squared. So as I said before, when n is very large, when the number of clients is very large, for example, 1 million clients, then this protocol becomes impractical. So we have to reduce that complexity in order to obtain a practical protocol. So the idea we use here to improve the communication complexity between the servers, it was observed in an MPC protocol by Ittai et al. In 2018. And the idea is that the communication cost of sum of product operation, which is actually a dot product between two vectors, is exactly the same as a single multiplication of shares. So it doesn't matter what is the size of the vectors that we do the dot product on. They have operating a secure dot product has exactly the same cost as just one multiplication, which is constant per server. So let's recall our example from before. We have 9 clients, each with its own row and column vectors. Now, suppose that by magic, each client picks a different location for its message, so there are no collisions. Now, we take a different angle on the secure computation that the servers have to perform. And instead of performing a secure computation for each client individually, they perform a secure computation for each entry of the global table. For example, for the entry 2,2, the servers compute that entry on the matrix for each client and add all results. So they first obtain the result of the location 2,2 on the full matrix for each client. Now, this computation is exactly the sum of product operation that I described before. Therefore, for each entry of the global table, we perform a secure sum of products, which has a constant communication cost. And overall, for the entire global table, we have a linear communication complexity, which is order n. And now it becomes much more efficient. In addition, by a simple rearrangement, we can describe the whole computation as a matrix multiplication, such that the first matrix has the column vectors of all clients, and the second matrix has the row vectors of all clients. Now, this is extremely helpful when performing this computation with a GPU, because matrix multiplication, the matrix multiplication operation is already heavily investigated and optimized over GPU. So in Blinder, we leverage that. Now, before I jump to the experiments we made, let me point out some things that I omitted in this talk, and you can find in the paper. So first, I did not say how to handle collisions of messages, where 2 or more clients try to write to the same entry. This can be solved by having each client send 2 blind messages, and the servers maintain 2 global tables. And the solution has only a small constant overhead. And the technique that we used to solve this was taken from riposte. The second thing is that a malicious client may send malformed blind message that occupies many indices, which might lead to a denial of service attack, like if he writes to all entries in the global table. Now, to prevent that, the servers run an additional MPC to verify the validity of the blind message. However, this verification raises another problem, because when detecting an invalid blind message, we have to decide on whether the client was honest and some malicious server wanted to frame it, or the client itself was the malicious. This decision is necessary in order to achieve robustness. And previous works use expensive tools like verifiable secret sharing to solve this. But in Blinder, we show that when the number of corrupted clients is sufficiently small, then we can achieve robustness even with simple secret sharing without resorting to the verifiable secret sharing. So let me describe the experiments we've made. So we tested the protocol with number of servers that ranges between 5 to 100, and number of clients that ranges between 1,000 and 2 million. And the message sizes we tested are between 32 bytes, which can accommodate secret keys, up to 10 kilobytes, which can accommodate small files. And as a reference, the standard Zcash transactions weigh about 1 to 2 kilobytes. So in that sense, Blinder can support transactions of anonymous payment systems. Finally, we experimented over both LAN and WAN settings, and using both CPU and GPU versions. So, okay, most of the Blinder protocol requires only peer-to-peer communication between the parties, but there are some parts that require secure broadcast. And for those parts, we used the open source Concord BFT protocol to achieve secure broadcast. So let me show you two examples of our results. In this figure, we compare between riposte in pink and Blinder over CPU in green and Blinder over GPU in black. So the comparison is done across messages of different sizes, from 32 bytes to 10 kilobytes. So just remember that the riposte protocol runs by 3 servers only and doesn't guarantee robustness nor censorship resistance. But riposte runs, in this example, by 5 servers and guarantees and has both guarantees. Now, as you can see here, the Blinder's CPU version already outperforms that of riposte. And the reason may be that the Blinder, the vast majority of the operations in Blinder are simple finite field arithmetics, whereas in riposte, most of the operations are AES, which are operations that require more CPU cycles in average per byte. Furthermore, the GPU version of Blinder is way faster. So the black line in the figure represents one epoch with 100,000 clients, whereas all other lines represent epochs with only 10,000 lines. So while this is only a factor of 10 between the number of clients, the impact is a factor of 100 in the computational complexity, because the computation in Blinder increases quadratically with the number of clients. So this means that we have about 100 times speed up by implementing Blinder over GPU, which makes it the fastest solution in the client-server model. The second example of our results is follows. So in this figure, we compare the latency of Blinder across varying number of clients. The green lines are for the CPU version, and they range from 1,000 to 100,000s. And the black lines are for the GPU version, and they range from thousands to, from 10,000s to 1 million. Now, there are 3 lines for each version. The bottom one is when Blinder is implemented with 5 servers. Right? The middle one is when implemented with 10 servers, and the top one is when implemented by either 100 or 20 servers. So the figure shows that in only 8 minutes, we can handle 100,000 clients with CPU implementation, or 1 million clients with GPU implementation. Okay? As a comparison, if you look at riposte, with 1 million clients, it would run for over 10 hours. And it is also estimated to run in the same, at the same time, even if it was implemented using a GPU. Because AES gains much of its efficiency because it is hardwired into the CPU, but it's not hardwired into the GPU. Now, you can see that both groups of lines are quite close to each other, meaning that the number of servers doesn't have a great impact on the latency. And this is because in Blinder, we shifted the bottleneck of the protocol to be the computation rather than the communication. And with that, I will finish. Thank you very much for listening, and hope to see you soon physically. Thank you.